Signals play a fundamental role in communication and signal processing systems. Understanding different waveform shapes and how they behave under various transformations is essential in analyzing real-world signals. In this presentation, we focus on the triangular waveform, its mathematical representation, Fourier series forms, and how it responds to different signal transformations using MATLAB, Simulink, and experimental demonstrations. A triangular wave is a periodic, continuous, and piecewise linear waveform. Unlike a sine wave, it is not a pure tone because it contains multiple frequency components. Its spectrum consists only of odd harmonics, and these harmonics decay much faster compared to those of a square wave, making the triangular wave smoother in the time domain. This slide shows the general equation of a triangular wave. Here, A represents the amplitude, which determines the peak value of the signal, while F represents the frequency, which controls how often the waveform repeats in 1 second. These parameters allow us to control the shape and timing of the triangular waveform. Any periodic signal, including the triangular wave, can be represented using Fourier series. In this presentation, the triangular wave is expressed in 3 forms: the trigonometric form, the combined trigonometric form, and the exponential form. Each form represents the same signal but is useful for different types of analysis. The trigonometric Fourier series expresses the triangular wave as a sum of sine and cosine terms. Due to the symmetry of the triangular wave, only odd harmonic sine terms appear in the series. This form is useful for visualizing how each harmonic contributes to the overall waveform. This slide presents the derivation of the trigonometric Fourier series. The Fourier coefficients are obtained by integrating the waveform over one period. Because the triangular wave exhibits symmetry, many coefficients become zero, simplifying the final expression. The combined trigonometric form rewrites the sine and cosine components into a single trigonometric expression. This representation simplifies mathematical manipulation and highlights the amplitude and phase of each harmonic component. Here, the individual sine and cosine terms are combined into a single expression using trigonometric identities. This form is especially useful when analyzing phase relationships between harmonic components. The exponential Fourier series represents the triangular wave using complex exponentials. Although this form may appear more abstract, it is widely used in signal processing because it simplifies analysis involving frequency spectra and system responses. This slide shows the derivation of the exponential Fourier coefficients. By expressing sine functions as complex exponentials, the triangular wave is represented as a sum of rotating phasors in the frequency domain. To validate the mathematical expressions, Simulink simulations were created for each Fourier series form. These simulations show that despite the different mathematical representations, all 3 forms generate the same triangular waveform in the time domain. This slide demonstrates signal transformations applied to the triangular waveform using Simulink. Transformations such as time reversal, time scaling, and time shifting are applied to observe how the waveform changes while preserving its fundamental shape. A MATLAB graphical user interface was developed to provide an interactive way to visualize triangular wave transformations. This tool allows users to adjust parameters such as amplitude, frequency, and time shifts and immediately observe their effects on the waveform. By adjusting the control parameters in the GUI, such as amplitude, frequency, and time-related operations, the corresponding changes in the waveform are immediately reflected in the output plots. This real-time visualization helps illustrate how each mathematical transformation affects the signal's shape and behavior. The GUI output confirms theoretical expectations. Time domain operations, such as time shifting and time scaling, alter the horizontal placement and spacing of the waveform, while amplitude operations affect the vertical scaling and polarity of the signal. Despite these transformations, the fundamental triangular shape of the waveform is preserved. This slide presents the electronic bench simulation of the triangular waveform. The waveform is generated and observed using practical electronic components, allowing us to simulate how a triangular signal behaves in a real circuit environment. The output closely resembles the theoretical and simulated triangular wave, validating the accuracy of the mathematical model. The electronic bench output demonstrates that triangular waveforms can be physically generated and measured using electronic circuits. Minor distortions may be observed due to component tolerances and non-ideal behavior, which are expected in real-world systems. Despite these imperfections, the fundamental triangular shape and periodicity of the waveform are preserved. This slide shows the actual experimental results for time-domain transformations applied to the triangular waveform. Time reversal produces a mirror image of the waveform, time scaling compresses or expands the signal in time, and time shifting moves the waveform along the time axis. These results confirm the theoretical definitions of time-domain signal transformations. Here, amplitude-domain transformations are demonstrated through actual experimentation. Amplitude reversal inverts the waveform, amplitude scaling changes the signal magnitude, and amplitude shifting introduces a vertical offset. These operations affect the amplitude characteristics of the signal without altering its frequency content. By comparing the experimental results with MATLAB, Simulink, and electronic bench simulations, we observe consistent behavior across all platforms. This agreement verifies the correctness of the theoretical analysis and demonstrates how signal transformations apply to both simulated and real signals. Overall, the electronic bench and experimental results bridge theory and practice, showing how triangular waveform transformations behave in real-world systems. In summary, the triangular waveform was analyzed through theory, simulation, and experimentation, demonstrating how signal transformations behave consistently across analytical, simulated, and real-world environments.